All right. Hi, subcourse QM5203, Edition A, Hydraulics and Pipeline Operations, and Army Institute of Professional Development, Army Correspondence Course Program, Readiness, Professionalism Through Growth. Lesson Introduction to Hydraulics, Critical Task 035103000024, and others. Introduction. Since machines were first introduced in the battlefield, military leaders depend on continual sources of petroleum power. These machines, in fact, throughout the many wars of the 20th century battles of the waters, wars have been won and lost based on the control of the fuel, and military weapon systems have become more lethal, and they have used to become vast consumers of petroleum fuels. In fact, the single U.S. Army Mechanized Infantry Division today uses over 1 million gallons of the fuel in a single day during the offensive operations. Our mission as the petroleum leader is to feed the very ravenous hunger of our military war machine. It is important to make every attempt to protect the environmental while it's still accomplishing the mission. As such, as you must conduct an environmental assessment from beginning fuel operations. The unit environmental officer coordinates with the EPA representative of the unit petroleum officer and the environmental regulators to make an assessment with the petroleum operation. The assessment is used to determine how the petroleum operation will affect the wildlife, local population within its units, areas, operation. Environmental compliance officers use the result of the assessment to verify whether or not the petroleum operation is in IAW and the prescribed environmental compliance. The unit environmental officer works with the following personnel: with the environmental compliance officer, the EPA officer, unit a petroleum officer, and environmental regulators. As with any operation, the unit environmental officer must stress the spill prevention. The unit environmental officer also responsible for knowing the governing spill and the contingency policy, installation policy, the CONUS policy, and or OCONUS policy, any host nation policy, and applies the to the area where the petroleum operations will be conducted. In the years of World War II, the U.S. Army Quartermaster's Corps has operated with the petroleum pipeline through the world locations such as Korea, Japan, Europe, Alaska. More recently, tactical pipelines have been deployed to support the Desert Storm, Somalia. Also, military experts such as Ravening Sands, Market Squares, Bright Stars, Tandem Thrust have been seen in deployment of tactical multi-product pipelines. Although often thought the insignificant during the peace war, all petroleum NTOs officers will find themselves in the field commanders during the wartime. Battles and wars hinge upon leaders' ability to bring overwhelming destructive firepower upon the enemy. Good leaders recognize that they must include petroleum leaders during the initial planning phase of the operation, otherwise they may find themselves in command of non-mission capable. All petroleum leaders must strive to educate supervisors of the importance of the adequate petroleum support. You must also teach your subordinates to understand to be able to execute their responsibility to support the force. One, the terms. Here are some of the terms and definitions we encountered during this lesson. Darcy-Washbeck equation used to calculate the friction head loss in the pipeline. The design fuel type in which the pipeline system is designed. The military pipelines will mostly likely transport kerosene-based diesel fuels and jet fuels. C, friction, loss of pressure in terms of the feed of the head of the per unit of the pipe length for the internal resistance to the flow of the product of its viscosity from the resistance offered by the pipe walls, pipe fittings, and reductions in pipe diameter. The Reynolds number, an equation used to determine the friction factor required in the Darcy-Washbeck equation. Specific gravity, a physical property of the liquid, the ratio weight of the volume liquid to the weight of the equal volume of water. API, gravity, the specified scale developed by the American Petroleum Institute, used in the petroleum industry that is based on reciprocals. 2. Basic petroleum mathematics. Know that you are familiar with the terms related to the petroleum hydraulics pipelines design. We will begin with the introduction to mathematics. As a student in the petroleum officer course, more importantly, the petroleum officer, you will encounter the problems requiring more than just basic mathematical abilities. These problems will require an officer to be able to not only solve the general problem or the given problem, but determine multiple unknowns along with the way which can be greatly affected the final solution. Mathematical evaluation designed to test not only your mathematical skills but also your analytical thinking abilities successfully. We must learn to understand the flow rates, velocity. We must learn to perform the basic calculation field related to flow rates, velocity, and velocities to determine mechanical hierarchies or mathematical hierarchies using rule mathematics. Solve the unknown variable given and all of the variables in the equation. Flow rate. Throughout the petroleum officer course, you will encounter flow rates, and the applicability of solving the petroleum-related problems is very important to understand what the flow rates are and how they are measured. Their significance to solve these problems. The flow rate can be defined at which measures specific volume of the liquid delivered on a specified period of time. Know that that the two most sufficient elements of the meaning of the volume and time, the flow rates, can be distinguished through the velocities, which we'll discuss later, by the unit of measure. 2. If known that the amount of the volume liquid amount of the time is measured, you can determine the specific flow rate of the liquid. Flow rates are generally denoted by the abbreviation Q. Volumes can be measured maybe many different units of the measurement. The most common one used in the petroleum industry is cubic feet and gallons and barrels. The most common measurement we use dealing with the flow of the rates in seconds and minutes and hours and days. 4. When putting the volumes of the measurement together with the unit of time, you do different measures of flow rates. Some of the more common flow rates will be discussed throughout the course are gallons per minute, barrels per hour, and cubic feet per second. Conversion of flow rates. Often working with the petroleum fuel, we require the flow rate that is given with the unit of the measurement converting to another order and solving the specific problem. For example, we are given the flow rate of the gallons per minute, but have they more converted with the unit of the measurement to barrels per hour to specify the scenario. Luckily, most flow rate conversions are required to make. They already have been figured out mathematically, placed in the field manual 1067-1 Appendix M. All you have to do to take is just take the correction unit of the FM 1067-1, multiple your answer in the converting flow rate. However, there may be some cases in specific flow rate is not listed with the reference manual. Therefore, we need to discuss how to perform these conversions so that you can understand how they are calculated. 1. Let us take an example. Solve the together problem. You can operate a hose line system. You can have a meter in line. You have received the 500 gallons over the past 2 minutes. Your supervisor needs to know how many cubic feet per second it equals. To solve, you follow the order. The first requirement example is to convert the time down to a minute measurement. Since we are dealing with 10 minutes divided into 2, converting by the multiple unit of the measurement of 500 gallons over the 2 minutes converted into 250 gallons per minute. Using the field manual 1067-1, Appendix M noted that converting the gallons per minute to cubic feet per second requires multiple your answer to by 0.00222. Multiplying the factor with 250 gallons per minute, you can determine the flow rate of 250 gallons per minute is equal to 0.557 feet cubed seconds, feet a second. What does the conversion come from? As the previous stated, important to understood, but the conversion factors of the field manual 1067-1 from the sense not all possible flow rates are listed in that reference. All units of measurement convertible as long as you know the characters. For instance, most people do not know offhand 1 hour equals 3,600 seconds, but 1 hour equals 3,600 seconds, but everyone knows that 1 hour equals 60 minutes and 1 minute equals 60 seconds. Multiply these two conversions together with quickly determine the 1 hour equals 3,600 seconds. Looking at the previous example, the flow of the rate of the gallons per minute had to be converted with the public feet per second. How was the conversion derived? One of the first things remembered is whenever we have the measurement unit of the numerator or denominator, only way to cancel those units is to put them into the other side of the fraction. Starting with the flow rate of the gallons per minute, we can write the flow rate as a fraction. Gallons over the minutes. The flow rate can be converted into cubic feet per second or cubic feet over seconds. Before the fractions down to see with the required converting the gallons to the cubic feet for the volume meter and minutes to the second for the time measurement. Gallons can be converted with the cubic feet, determining the number of the gallons in the cubic feet. The number is 7.48. There's 7.48 gallons in a cubic foot. So if you start your fraction gallons over the minute, multiply that the 1 cubic feet is over 7.48 gallons. You can cancel out the gallons measuring into the numerator denominator. You're left with 1 cubic feet over the minutes multiplied by times 7.48. For minutes and seconds conversion, simple multiplying the fraction 1 minute over 60 seconds. This cancels out the minutes of the equation. You are now left with the unit of the measurement, the cubic feet over the seconds. Just then were composed to convert the rest of the math and problem. Along with the factors, you have multiplied one by the numerator, and multiplied 748 by 60 in the denominator. This equals 1 over 448.8 or 0.00222. Which is a conversion factor found in the field manual 1067-1, and Figure 1.1 illustrates how to accomplish this action. Where did the conversions come from? Gallons over minutes equal cubic of the feet and cubic over feet. Velocity like flow rate. Usually the one measurement over the another will the flow rate measure the volume of the liquid over the time. The velocity distance traveled over the time. More simply stated, is measured by the speed of the common abbreviation velocity is v. Distance of common measured in miles and feet and inches. However, they must also be converted to metric measurements since the denominator of the velocity is hours and seconds, etc. The same as the flow rates. Common velocities will use in the petroleum field of miles per hour and feet per second. Since there is no conversion for velocity listed in the field manual 1067.1, you must convert the velocity by hand by using the same process that you use to convert the flow rates. A. The instance required for the conversion from the miles per hour to feet per second is the conversion for the flow rates, both in the denominators and the same type of the measurements of the distance. Both denominators are measured in time. To convert the miles to minutes, to convert miles to feet, multiply 5,280 feet over 1 mile. This allows the elimination of miles, leaves you with a 5,280 multiplied by the feet over the multiplied by 1. Converting the 2 hours and seconds down by 1 to 2 ways. If you have 1 hour over 3,600 seconds, then you can multiply 1 hour over 3,600 seconds to eliminate the hours. From this equation example, to use the second method, first breaking hours down to 60 minutes and then breaking the minutes down to 60 seconds. Once the conversion is completed, we have now correct units for the feet over the seconds. At this left, to perform the math calculations, one numerator side multiplies the 5,280 times 1, and the other denominator side multiplies 60 times 60. The resulting of 5,280 over 3,600 equals 1.47 feet per second. Thus, the inferential mathematics we will conduct that for every 1 mile per hour distance traveled in feet per second equals 1.4 seconds feet per second. Area is the unit measurement defined inside the figure. The different type of the figures, each of the equation for the figure of the measured object also is measured in the square units. For instance, we may measure the areas of square feet, square inches, square miles. The areas of squares and rectangles are easy to determine. Just multiply the length of two adjacent sides to determine whether the inside the figure. The squares which have all the equal sides, just multiply the length of one side twice to determine the area. To determine the area of the circles is more difficult since the individual round area the mathematicians come up with the unit measurement to figure the area of the circle, which is labeled as or pi ratio. Circumference of the circle to the radius, also known as pi, is equal approximately 3.14, which means any given circle is the circumference will always be 3.14 the times greater with the radius. Commuting the area of the circle can be performed in one of the two ways. The first way would take the radius and squared and multiplying product with a pi 3, 4, and a quarter. If you do not have the button on the calculator, the second way to multiply pi times the diameter square d over the hours of 0.785 times the diameter squared, measuring the units agreed both in feet and both in inches, etc. Example: although determining the area of rectangle square fairly straight and forward may determine the area of the circle to become demanding to illustrate, we determine the area of the circle two different ways. For example, we find that the area of the circle the square inches have diameters to feet. After the calculation, multiply the radius 1 foot squared 1 foot squared by 3 1/4 inches of the area in which the 3 1/4 by 5 feet squared. To convert the square inches, multiple number of the square inches in 1 foot 12 times 12, 144 multiplied by the answer of 3 1/4 3.14 feet squared. The final answer is 452 feet 452.16 inches square inches. Before calculating, convert the radius of the feet into the inches. 1 foot is equal to 12 inches. 1 foot is equal to 12 inches. The most of the radius squared is 144 times pi. The answers are 452.16 inches squared. Solving the unknown variables. The last major section we must discuss is the solving unknown variables with given the equation multiple variables and over the variables is known. But the equation can also be solved by the unknown variable. When solving the unknown variable, always delete all the variables from the side of the equation. Separate the unknown variable. The important remembering thing when solving the unknown variable, it is deleting the other variables one side of the equation. You must perform the opposite calculation to remove the variable before solving the unknown variable. It is important to understand the hierarchies of the mathematics to correctly solve the equation. The correct hierarchies are as follows. Perform all the sections in parentheses. 2 exponents in the equation. Perform the calculations directly after the parentheses if there are any parentheses in the equation. 3. Next, perform all the multiplication division required. Always perform these functions from left to right in the equation. Finally, perform any addition subtraction required for the equation. Again, perform all the addition and subtraction functions left to right in the equation. For example, perform the following equation using the mathematical hierarchy. 1 plus 10 minus 2 times 9 divided by 62, and plus 1 is equal to x. According to the hierarchies, the math, the first calculation performed, the calculation parentheses 10 minus 2, which equals 8. The equation needed by 1 plus 8 times 9 divided by 62. Now perform the required exponent calculation. 6 squared equals 36. The equation now reads 1 plus 8 divided by 9, 36. The performing multiplication division for left or the right of the equation, and the first equation should be 8 multiplied by the 9 equals now remaining 1 plus 72 divided by 36 equals x. Performing all the multiplication division functions, 73 divided by 36 equals 2. The equation now reads 1 plus 2 equals x. The final calculation, addition, subtraction, 1 plus 2 equals 3. Thus the solution equation is 1 plus 10 minus 2 times 9 divided by 62 is x equals 3. Solving the unknown variables now that they have discussed mathematical hierarchy, solve the equation for the unknown variables given the following equation. Solve variable a plus b times x times y equals c. Show the proper way to solve the problem. C times x times y equals a plus b divided times c. The c is then canceled out of the right side of the equation, leaving you with c times x times y equals a plus b. To remove the b from the right of the side of the equation, subtract the b from both sides, leaving them without. Leaving us with a equals c times x times minus yb. Calculating fuel characteristics using mathematical formulas is very important to understand the concept of API, gravity, specific gravity, before calculation. It will give a much better understanding what the calculations mean. With the understanding of the concept, the function definitions can be found with the Field Manual 5-482, Chapter 4 in this glossary. Specific gravity is the physical property of liquids. Specific gravity is the ratio of the weight of the volume liquid is the weight of the equal volume of the water. API has given it a 60 degrees Fahrenheit specific gravity of 1.0. Traditional petroleum fuel oils, lubricants are lighter than density than water, thus have a specific gravity less than 1.0. For example, the MO-gas has a specific gravity of 725,000 10,000ths, which is computed by the comparing of the weight of 1 gallon of MO-gas of 6.04 pounds to 1 gallon of water at 8.33 pounds. The API gravity is scaled using the petroleum and industrial base of the reciprocal specific gravity. Therefore, the procedure will rule the number with the greatest numerical spread. Both API gravity and specific gravity measures the density of liquids. During the period of prior blocks of the instruction learned with the API, established arbitrary scales to express the gravity density of the liquid petroleum products. Each fuel takes on a certain range of the API gravity values, as shown in Figure 1.3 below. API shows the gravities from 1.0 to 0.722 and the API gravity 0 to 80 with the fuel lubricant oils, diesel fuel solvents, kerosene, JP, JPA, MO-gas, and avgas. As seen, you see the chart of specific gravity ranges for the major fuels, oil, lubricants. We use a military system number at the top of the chart of the AP ranges, while the numbers at the bottom of the chart show a few specific gravity ranges, as would seem to the fuels and oils, lubricants of the heaviest petroleum products we use are newly and dense as water. Calculate the API gravity at 60 degrees Fahrenheit. Normally, the API gravity reading will be at some temperature other than 60 degrees Fahrenheit. To convert the API gravity reading to 60 degrees Fahrenheit, the ASTM table 5B with the left and the right of the margins of the table are noted with the temperature of the sample. The upper margin listed with the API gravity reading. Once you have located the temperature value of the row across the unit, across until you intersect the column of the AP value with the insurrected value of the API gravity corrected with the 60 degrees Fahrenheit. So get the correct answer for the following set of data to determine the API gravity at 60 degrees Fahrenheit. See if you get the correct answer following the set of the data. Determine the API gravity for 60 degrees Fahrenheit. The observed API temperature of the API is 3778 at 38.7, 4648 at 47.1, 5260 at 52.0, 6650 at 67.4. Calculate specific gravity. The specific gravity is the liquid ratio, liquid weight. This weight of the equal to water. Again, the measurement of the density of the liquid is Sg the fuel by S. The SW the fuel and SW water. The SW water is 8.33 pounds per gallon. Specific weight of is the fuel weight, fuel volume, pounds and gallons converted with the formula. The form and values are used. The conversion of the API gravity, specific gravity, 1.415 to 1.415 API gravity is equal to, and 131.5 specific gravity. The specific gravity AP1 plus 135.5. See if you convert the answer to the following set of data, converting the following APIs into the APIs. Specific gravity of 10 is equal to 1.040 is 82.51. 65 is 72.0. Converting the following specific gravity into the API specific gravity, 8.84545 36.1 0.725 0.725263.6 0.811242.9. Volume correction is 60 degrees Fahrenheit. Volume correction of the correction is measured with the quantity of the product, determine the gauging, observe the temperature, gravity reference with the gauge of the table net, quality of the product of 60 degrees Fahrenheit, deducted from the bottom of the water sediment, and determine the API degree at 60 degrees Fahrenheit using the average temperature of the product of the tank, measured during the gauging, corrected the fuel volume using the volume correction factor to obtain the ASTM table 5B, corrected with the volume inch over the minus the bottom of the sediment, water equals the CF. Feet of head, the measure of the pressure to determine the height of the column given the fuel is known with the feet of head, or HF, which is directed with the correlation of the pounds per square inch. It is useful to use the petroleum field in which we can measure the friction loss pressure over the distance of the feet of the head, while the PSI can only measure pressure at one given point. Converting feet of the head with the PSI, feet of head times the specific gravity by PSI is equal to 2.31. Converting the PSI feet of the head, 231 times PSI of the feet of the head is equal to the specific gravity. Determining the feet of the head for the pressure per square inch, the specific gravity, and head feet of head. 20 is equal to 0.750, and 63.7. 60 is 0.8420, 164.6, 100 is 0.8035 to 287.5. Determine the pressure of PSI and the head of feet of head and specific gravity in PSI. 120 0.7040, 36.6. Feet of head of 205. The specific gravity is 7777. PSI 69.0. The feet of head 500 0.8250 for the specific gravity and 178.6 at the pressure per square inch. Basic principle of the multiple military pipeline system. Now that you've refreshed your memory on the basic mathematical operations, you should feel comfortable with what is to come. After all, one of the most complex, challenging, interest aspect of the petroleum operation is studying the hydraulics. You now know the basics that will lead through successful completion of the course of the provided valuable guidance knowledge of the use throughout your career. The petroleum leader had lost due to friction. Advantages and disadvantages of military pipelines. There may be advantages to the distributing method of the unique liquid logistics. However, the pipeline hose line live in their limitations. Also, below we discuss advantages of pipelines over the advantage over the conventional means of the transporting petroleum products. From an economic standpoint, the pipeline is the less expensive means with which to send large quantities of the product over the distances. Pipelines are all-terrain methods. Are all-terrain modes of transportation which all access of the areas not suitable for the other transportation. Pipelines relieve the burden of the fuel transportation from the railroad nets, which are more expensive and congested. Remember that approximately 60% of logistical tanks is bulk petroleum. One or current tactical pipeline in the Aipd can be delivering almost 1 million gallons of fuel forward every day. This frees up at least 200 military tankers to move forward with the support of the tactical fight. The pipelines are often extremely poor targets for the enemy aircraft. Pipelines can damage repaired with faster than damaged railroads or highways. Pipelines operations are not effective by adverse weather conditions. Pipelines usually release a large number of the personnel vehicle, logistical activity. Disadvantages of pipelines are subject to distribution, sabotage, and guerrilla attacks. Marine terminals, pump stations, and tank farms complexities are attractive targets for the enemy air and missile target attacks. Locating leakage and damage is time-consuming. The pipeline construction rate may lag behind the rate of the combat advance. The future role of the military pipeline system, although facing the modern war, continues evolving. One more that remains certain of For the next several decades, our military machines will continue relying only upon petroleum fuels, as which one of the doctors must continue expanded to meet the new missions bulk supply concepts. Conventional warfare or large-scale military operations will be supplied with the bulk fuel upon or near front lines of reasonable expected. The packages will be used as a supplement to bulk supplying methods when supply forwards are not accessible to bulk fuel transports. In some cases, when the rapidly advancing tactical situation dictated the need for the additional fuels to exploit the situation. To some extent, some of the fuels may be packaged strategically and delivered directly into the combat theater to end the use of regardless through output will use in so much as possible bypass level storage and velocity forward is the key. Petroleum products will be shipped overseas. The ports harbor the beachheads of the large tanker. The fuels will be pumped to shore for the use of the marine dock facility, submarine and underwater pipeline with the floating pipeline lighting in the tanker. They use the large flat bottom barges to shore with the product that will be made of the marine terminal storage and facilities constructed to offer the product of the target with the possibility to ensure the product security to meet the requirements. Facility may consist of the existing commercial marine terminal, boardable, bolted storage, steel storage tanks, or collapsible form fabric storage tanks. Obviously, there's not only solutions to bulk storage problems in the future. From the marine terminal storage facility, fuel will be pumped through forward to pipelines to large immediate head terminal tanking farms and forward areas using fine and collapsible drums, collapsible flexible hose line system, large capacity cross-country mobile dispensing vehicles, as well as the all tanker truck, trailers and pods. The concept of warfare will be employed the pipelines in much of the same way as during the World War II, the Korean War. All the equipment and technology change. The concept does not change the employment. However, it will require increase the quantity of fuel and pipeline system capable of quick deployment and emplacement. Limited nuclear warfare will modify the use of the military petroleum pipeline system. More reliance will be made upon the dispersing storage collapsible fabric storage tanks rather than high vulnerable underground above-ground fixed facilities. Also, the use of flexible hose lines systems will be expected to increase during the limited nuclear warfare. Unlimited nuclear warfare will place great emphasis on stabilizing an area, capitalizing the existing facilities, which will be used depending on the state of the repair. All in all, the bulk supply concept will still be needed to perform. 3. The pipeline system consists, classified according to the pipeline system, the following 3 general types: assault, tactical, logistical. Assault type in the system is generally temporary system which can quickly install provided with the petroleum product with rapidly moving the combat situation. A tactical system is one that can be rapidly constructed with relocated in order to provide sufficient fuel to the large area of the scope of the operations. The logistics system is more permanent pipeline designed to provide quantities of fuel to be stabilized in the area. B. When classified according to the construction, pipeline systems also fall in 3 general types: hose line, coupled, and welded. All 3 methods of construction may be found in the military bulk distribution system. Usually the construction type of the parallel of the classification hose line system is constructed with the collapsible hose mounted at the rapid play. It is made with a temporary extension of the lateral from the more permanent location of the pumping. The unit is portable with relatively low flat flow rates and pressures. Coupled systems are constructed with the stringing of the pipe and the placing of the pipe along with the route, then stovepiping it in one joint at a time like a chimney stovepipe. Various coupling of the methods may be used, including bolt joiners and mechanical clampers. Welded construction is also used excessively with the civilian industrial petroleum application. Comparison welded construction in bulk military distribution systems used largely ship-to-shore tankers unloading the lines of the submarine or dock at the locations where the situation dictates buried pipelines. See Army pipeline responsibilities. While many personnel think of the pipelines are purely quartermaster mission, the truly team and effective more among several branches of the service as discussed below. The quartermaster's responsibility are to establish the petroleum oil lubrication requirements for operation military pipeline system, provide organizational level maintenance of the pipeline system once in place. Engineering corps of the petroleum outline oil lubricants responsibility include design, construction, maintenance, maintaining pipelines, bulk storage facilities, marine terminal facilities, fixed dispensing equipment, other technical service responsibilities. A transportation corps responsibility for the movement of petroleum oil lubricants by means other than pipeline or local distribution. The Ordnance Corps maintains the form of the petroleum production specification because of their role as the developer, maintain engineers for the requiring fuel. The Single Corps provided the communication support of the pipeline operations design fuel. Before we build any pipeline, many factors must be taken into account. The first, we discuss the design of the fuel. The definition of the design fuel is the heaviest, making up to 47% or more than total annual fuel requirement. Because below is an example of how to determine the design of the fuel. Will be given the following total annual fuel requirement for the theater of the fuel. JPA GP8 at 1,200,000 barrels, diesel fuel at 900,000 barrels, MoGas at 1,600,000 barrels, and for a total of 3,700,000 barrels. Divide each product by the total of barrels. GPA is 32.4%, diesel fuel is 24.3%, and MoGas is 43.3%. Discard the consideration note mentioned criterion of the 24% or more. Here, however, the three products met the criterion of 24% or more. We now determine the product of the heaviest is yielding fuel, manual 5482, the table 41, finding the average specific gravity for each of the product. Since diesel fuel is the heaviest product, it will become the design fuel. Theory of flow study for the characteristic of the liquid motion. This is the particular importance with the design pipelines to ensure the correct placement of the pumping station along the pipeline can maintain the desired flow rate. Well, we understand how the flow rates are affected with the friction head. There's several steps which must be designed to determine how low head loose the friction head or head of understand with the head of friction. Understand when the liquid moves from the pipe, the friction occurs between the liquid of the inside of the pipe of the wall. The friction will cause the liquid to slow the advance forwards. We can overcome our head loss due to the friction. It will now be what the head loss will be given the distance to be the Reynolds number, the pivot formula, in determining overhead losses during the friction. Remember, the Reynolds number is dimensionless. 1. The effective pipe of the diameter internal force of the viscosity forces is considered with the Reynolds number. The two formulas can be used to determine the Reynolds number depending on whether the pipeline is development stage or is in place. The pipeline is development using the design data formula, otherwise use the field data formula. A formula of Reynolds numbers use the design Reynolds number versus the velocity of the per second by the times the diameter and pipe in the feet. Y is the kinetic velocity of the square feet per second. B is the formula of Reynolds wrapper using final field data. The Reynolds number is equal to 3,160 times the flow of the rate of the gallons per minute, where 3,160 constant times the inside of the diameter of the pipe times kinetic velocity and sent to Stokes. Now let's solve the problem. Given the following data to determine the Reynolds number using the design data formula. The velocity of 540 feet a minute, the ID of 6.4 and 15 inches, the fuel of the diesel fuel at 50 degrees Fahrenheit, finding the velocity in feet and seconds. 540 feet times 1 minute equals 9 feet a second. The minimum of 60 seconds, finding the d feet and 6.4 and 0.5 times 1 foot is 0.53 and a fourth, 5.534 feet and feet. 12 inches is find the y in feet and seconds squared. Field manual 5482, figure C7. 4.9 CS is equal to 0.0000527 feet squared. Seconds are 92,900. Solve the Reynolds number. 9 feet seconds times 0.534 equals 91,195.446. 0.00527 feet squared second. Finally converted to the specific notation, or 91,195.446 times equals 9.12 times 104. Now let's solve the problem using the field data formula. Given the following data, in the reusing the field data, the formula the quantity. The flow rate of the gallons per minute. Flow rate of gallons per minute, 350 gallons. The distance is 6.4 and 15 inches. The K, the JP40, the gas is JP40 at 50 degrees Fahrenheit. Solve the 3,600, 3,160 and times 350 is 1,106,000 equal to 144,000. 881, 60 times 415 times 1.19, 7.63385. Converting the specific notation is 144,881 equal to 1.45 times 105. Remember that you know how the Reynolds number the time to interpret the put into the good use design the military pipeline. Quite simply, put the Reynolds number in use to determine the type of the flow, and the pipeline broke down with three categories: one or 0 to 2,000 laminar, smooth or well defined 2,000 to 4,000, transitional not smooth 4,000, and upper turbulent chaotic non defined. In multiple product pipeline, the turbulent flow is desired to reduce the size of the interface by reducing the amount of product mixing during the flow. Determine the friction factor with the pipeline. Friction factor is function with the roughness of the pipe. The Reynolds number. The friction factor is determined using the Reynolds number nominal pipe size. Figure C8 and field manual 542. The given the flowing information determine the friction factor. Reynolds number equals 8.0 times 104. The 4 is the nominal pipe size. The equal the friction factor of 0.21. Determine the head loss due to the friction. The head loss due to the friction. The Darcy-Weisbach equation is used to determine the head loss of friction, as well as the Reynolds number. The equation, the two formulas designed and modified, shown below in the figures. All right, H is your head loss is equal to the friction over the factor times length of the pipe in feet times the velocity in feet in second squared, E divided by 64.4 times the diameter inside of the diameter in feet. The head loss is equal to 0.31 times the friction factor times the length of the pipe in feet times the flow of the rate in gallons per minute divided by the inside of the diameter in the inches to the fifth power. Given the following, determine the head of the friction loss. The design of the pipe is 0.701 feet. The fuel is diesel fuel at 50 degrees. The velocity is 4.0 feet a second. The length of the pipe is 4,000. First must be defined to determine the Reynolds number. The Reynolds number is equal to the velocity times the distance. Y. Velocity is 4.0 point seconds, 701. Given the diameter, the Y is 4.9 centimeters, centilars or whatever. You get 0.00527 feet a second, and 9,290. Redo the 4.05 section of times 4.05 the foot seconds times the 7.701 feet, and you get 53,206.8 or 55.3 to the 10 to the fourth. From the FM 548, the C8, the figure, the friction loss is 0.216. The head friction loss is 0.216 times 4,000 times 16, 1,382 feet, 4 feet, and 6 times 64.4 times 701 equals 45.144. The head friction loss is 30.62 feet. Given the following, determine the head force of using the field modified formula. Pipe is 8.415. Fuel, diesel fuel at 50 degrees. The 4,700 gallons per minute. The pipe length is 400 feet. The first, you must find the friction loss. Determine the yields number. The read 31,600 times the gallons per minute times the distance times the K. 700, 800, 415. Alright, from field manual 482, figure C8, and the F is 2 of 16, determine the D, the appendix C, the table, the ACCP 5203, the P, C1, 8.4555 equals 42,196. The head friction loss is 0.31 times 4,000 times 490,000 equals 1,312,416, or 42,196 and 42,196. Finally, you find the total head loss due to the friction at 31 feet. Alright, advanced hydraulic mathematics. Now you have the basic understanding of the reason for the pipeline, general characteristic property of the petroleum field. Next, we will attempt to familiarize yourself with some of the advanced petroleum math computations that will help you in your future petroleum assignments. Specifically, you will be able to calculate volume correction, head of flow, velocity, flow of the type, head loss. You must be able to quickly apply each of the principles you learned thus so far before you can begin physically designing a pipeline hose line. Therefore, thoroughly a problem-solving exercise must be completed. Let's begin. Volume correction at 60 degrees Fahrenheit with the correction is measured with the quantity of the product with the net quantity at the product with 60 degrees Fahrenheit, deducting the bottom sediment in the water. After deducting determine the API of the degree of 60 degrees Fahrenheit, using the average temperature of the product measured during the gauge in the tank, correcting the fuel pump Correcting the fuel volume by using the volume correction factor obtained with the ASTM Table 6B, but the correction factor is used as the multiplier. Correct volume by the inch of the minus the bottom sediment water times the correction factor calculated with the corrected volume of the 60 degrees Fahrenheit. All right, the data inch is 24,816 gallons. Bottom sediment water is 240 gallons. The API gravity is 60 degrees is 58.5. The average temperature is 70 degrees. Solution of the corrected factor is equal to 0.9932 at table 6b. The corrected volume of the 24,816 minus 240 times 0.9932 equals 24,576 times 0.9932 at 24,409 gallons. The feet of the head, the measured pressure in terms of the heat of the column, the given the fuel, known as the feet of the head or the HL, the pressure specific pressure in square inches times the height of the feet times the specific gravity height equals 23.1. Pressure of the gauge is 2.31 special gravity. Problem determining the feet of the head, solution pressure square inches, specific gravity, and head of the loss of it. The feet of head 25.725, 79.750 for the 8.420, 137.2 at 100 square psi. The specific gravity 0.835 in the head loss. The feet of head is 287.5. The problem determining the pressure specified with the solution. The head loss of the 100 is 0.704. Specific gravity 30.5 psi. 250 head loss. Specific gravity 7.7777 psi. 84.2, 500.825. Specific gravity psi 170.8.6. Velocity of flow is if the flow speed usually measured with the feet per second equals the flow rate, the cubic feet per second divided by the cross-sectional area of the pipe at the square feet, equals the velocity of the pumping per minute, the times the cross-sectional area. The area is 0.78.5 times the diameter squared times diameter equals the diameter is inside of the feet of the problem. Determine the flow of the velocity of feet per second. The data is 1,000 barrels per hour. The data is 6 inches. Solution is 1,000 barrels times 42 gallons times 1 foot per third. 1 foot 3 times 1 hour times 1 minimum. It gets you a 1 hour 7.48 gallons times 60 minutes times 60 seconds. The diameter 6 inches and 1 foot feet and 12 inches. The area 7.85 times is 0.52 equals to 2 feet. It's 0.2 feet. 2 velocity 1.578 and 78 feet per second. So, I'm sorry, I copied the charts and they didn't come out like they should have, like as equations. The flow type, there are 3 types of flow: laminar, transition, turbulent. And find out the flow type of the military pipeline. Reynolds number, the formula, the reformula using the data formula, the reformula of 3160, and for the flow rate, where the flow rate equals the flow rate of the gallons per minute, the distance times the K, velocity in sanitized strokes times the diameter. Inches, the K is velocity of center strokes, CST, to the reformula using design of the velocity times the diameter times the velocity in seconds is where the velocity in foot seconds, the diameter inside the diameter in feet, and the the velocity in foot in seconds. And flow, the type of remember the different type of the flow is maintaining the determinate flow with the multiple product of the Reynolds number, the flowing the type, the zero is less than the re is greater than 0 and less than 2,000 lamimeters. 2,000 lamimeters is greater than is less than RE, and 4,000 transitional, 4,000 re-turbulent, and preferred military pipelines. Problem given with the velocity of 3.7 miles per hour. The ID is 6.145, and the viscosity of 0.08 feet a minute. Calculate, redetermine the flow type of the situation. The velocity of 3.78 miles per hour times 5,280 feet a mile, 1 hour, 3,600 seconds, 5.43 feet a second. The ID of 6.145 times inches and 1 foot and 12 divided by 12 is 0.5112. The velocity is 0.08 feet a minute. The times 1 minute 60 seconds times equals 0.013 feet a second. And read that 5.43 times 0.512 is 2,001 2,138 transitional or 003 given that the V is the problem. Given that V is 5 miles an hour, the idea of the 8145, the velocity of 12 feet in the 2 minutes, the calculator redetermine the flow type of the situation. Solution: the velocity of 5 miles an hour, the 5,280 feet per mile, 1 hour, 3,600 seconds, 7.3 feet a second. The idea of 8145 at 1 foot at 12 inches, 0.679. The velocity of 12 feet in 2 minutes, and then 1 minute and 60 seconds is 0.2 feet in 2 seconds. That 7.3 at times 6.7 and 8 is 24.8 laminar, 0.2. Problem given with the 500 barrels per hour, ID 6 inches, the 42 centi-stokes, calculated, determine the flow, the type, the solution, the quantity, the pressure is 500 for 4260 of the cannon strokes equal to 350 gallons per minute. 3160 times 350 is 4,389. Turbulent 6 times 42. Alright, this keeps going on. The head loss of the pressure of the pipeline due to the friction measured from the feet of the head. The most accurate method of the head loss is using the Darcy-Weisbach equation. Darcy-Weisbach equation design model of the head loss of the equal to feet. The flow times the length times the velocity, whether the friction factor addition, friction dimension times the length times the velocity twice. This equals 6.4 times the distance times the length of the pipe length of the feet. Velocity of the feet per second of design. D equals inside the diameter of the Darcy-Weisbach equation. Modified model of the head loss is equal to 0.031 times the friction loss times the length times the flow rate squared with the friction factor. The diameter times 5 equals the length of the pipe length feet and quality of the flow rate of the G gallons per minute with D inside the diameter. Problem given the friction is 0.035, the length is 0.5 a mile, the velocity of 3,000 feet per minute, the diameter of half a foot, and specific gravity of 0.8260. The head loss in psi, the length is 0.5 times 5,280 feet in a mile, 26,400. Half a mile, 300 feet minimum at 1 minute 60 seconds, 5 feet a second. The velocity of 25 feet a second. The head loss is 0.35 times 26 times a half a mile times the velocity of 25 is 71.7 feet. 64.4 times a half a psi. The head loss of the specific gravity 71.0 times 0.8260 equals 25.7 or 2.331 or problem given with the friction loss of 0.92, length of 2 miles, pressure, the 300 barrels an hour, the distance of 8 in the LWST, and specific gravity 0.8448, the head loss in PS. Alright, the solution: the length of 2 miles, 2 miles is 10,560 feet. The 3,000 barrels an hour at 42 barrels, and 1 times 160 hours is 210 gallons per minute. The 4,410 barrels, diameter 5 times 5, 3,276 8, head loss 0.031 times 92, 10,560 times 41 times 100, 315 feet. 4,200, 196 psi equals the head loss of the specific gravity equal to 315 times 0.8448, 115.2 times 231, 231. And that's the last of the hydraulics pipeline operations. Of course, QM 5203 Edition A, Army Institute Professional Development.